Hello viewers, welcome back to our series of lectures on Unit 1 of the course CH202 of the second year BSc curriculum of UGC. In today's session, we will continue our discussion on IR spectroscopy, and we will focus attention on primarily two things: one, the origin of IR spectrum, and second, the measurement of IR spectrum. And the session is planned as follows, that is, to begin with, we will briefly review what we did in the previous session, and then thereafter we will look into the origin of IR spectrum, and this will be kind of tailored in the following way, that is, we will start with what is the energy level diagram for a vibrational motion, a molecule which is executing vibrational motion, and the quantized energy level diagram, what kind of diagram is there. And then we will see that what are the selection rules which allow us to find out what are the transitions which are possible there. Then we will see out of the possible transitions, what are the transitions which can be observed. Having done that, we will look into what are different vibrational modes of a molecule, and then we will see the origin of bands in the IR spectrum. Having done all this, we will move on to the measurement of IR spectrum, and in this context, we will take up in little details about sample handling, because sample handling is very crucial in IR measurements there. And towards the end, we will give a brief description of the dispersive IR spectrometer, the spectrometer used for recording IR spectra. And then towards the end, we will try to sum up what we do in today's session. So with that kind of an outline, let's start by recalling what we did in the previous session. What we did in the previous session was, we basically defined what is IR spectroscopy and then described the regions of IR part of the EM spectrum. Having done that, we moved on to outlining the importance of IR spectroscopy, wherein we said that in what all possible ways can we make use of IR spectroscopy, which we will be talking in details at a later stage. Thereafter, we discussed that how do we model molecular vibration, because we know that IR spectroscopy basically deals with interaction of radiation and matter, and in this particular context we find that IR radiation basically induces transition amongst the vibrational energy levels, or the vibrational motion of the molecule is perturbed by this. Then in this process, we also made a mention of the expression which is there for kind of working out the vibrational frequency, and we realized that this happens to depend on two important parameters. One, the force constant given as K, which actually is a measure of the strength of the bond, and second happens to be mu, that is the reduced mass there. Then we explained the characteristics of IR spectrum. We took a spectrum, a schematic one, and showed that the spectrum can be characterized in terms of the different kind of bands what we get there. So they are characterized whether there are strong bands there, or weak bands, or medium bands there, and things like that. Thereafter, we discussed the condition, what is necessary for the spectrum to be observed. That means, what is the requirement in the molecule so that the molecule can interact with IR radiation and give us the spectrum, which can be made use to find out the information about the molecule. So that's all have been done in the previous session. Now continuing from there, let's get into little more fundamental things, that is, what is the origin of IR spectrum. What basically we are going to do, as I mentioned earlier, is that we will try to see here that the vibrational motion is quantized. Let's understand the meaning of this. What it means is, we made a mention in the previous session that there is no molecule which is completely stationary. All molecules are executing at least vibrational motion, if nothing else. So when you talk about vibrational motion, if I try to kind of treat this vibrational motion in terms of quantum mechanical prescriptions, we find that the vibrational motion of the molecule is quantized. What it means is that it can vibrate only in certain possible ways, and that actually is represented in terms of an energy level diagram which goes as follows. That is, this basically is a representation of different possible energy levels of a vibrating molecule. We will not get into details of this expression here. About the details of this we will be learning in your third year when we talk about vibration spectrometry in terms of the physical part of it, the quantum mechanical treatment of that. For right now, it suffices us to know that the vibration motion is quantized. Probably I would like to make a mention here that the quantization we are familiar with. We know that in case of atom, we know that electronic energy is quantized. So what it means is that in the atom we have a nucleus, and electron can take up only certain energy levels. So the meaning of quantization is understood to you. But in this context, when we are talking about vibrational motion, what we are trying to say is that the vibration of molecule can be done, or a molecule can vibrate only in certain allowed ways. It can take up only certain energies, like in case of atoms, the electrons around that. Okay. So, that is the meaning of the statement that vibrational motion is quantized. Now, we have a selection rule. This again is a quantum mechanical term which basically tells us that, because when you said that vibration motion is quantized, we have got different kind of quantum numbers there. We must have seen that V is equal to 0, V is equal to 1, V is equal to 2. So, there are different energy levels. Like in case of atom, we have got the principal quantum number, n is equal to 1, the first shell, n is equal to 2, second shell, and so on and so forth. So, similarly here also we got different vibration quantum numbers as V here. And the selection rule tells us that what are the transitions which are allowed to take place for a molecule which is whose vibration motion is quantized here. And the selection rule happens to be that delta V is equal to plus minus 1, plus minus 2, or plus minus 3, and so on and so forth. What it means in turn is that if this is my energy level diagram, wherein these are the different vibration energy levels there. So, these are the following transitions possible there. That means, if the system to begin with is in, say, V is equal to 0 level, it can go to 0 to 1, 0 to 2, 0 to 3, and so on and so forth, or maybe from 1 to 2, 3, and so on and so forth. All transitions are possible. That is, as per the selection rule, we work out that from any kind of a vibrating molecule, we expect a large number of bands, probably infinite, because this number is not limiting anywhere, it goes till infinity. So, that means in principle, any molecule can give us an infinite number of signals there, which in fact is not true. So, let us see why is it not true. It is not true because of the reason that what actually happens is only a few of these transitions are actually observed. Theoretically speaking, all the transitions which I just mentioned are allowed. That is, the selection rule permits that transition to be there. But what actually we observe is only a few of them. The ones which we observed is this transition here from level V is equal to 0 to V is equal to 1 level, and this is termed as the fundamental vibration. So, for a given molecule executing given vibrational mode, this frequency is the fundamental frequency which will be observed in the spectrum. That means that basically pertains to a transition from V is equal to 0 level, that is a ground state, to the first excited state level there. So, that is what is allowed there. Or we may have 0 to 2, that is, this is called as first overtone, and 0 to 3 is called as the second overtone. So, this will be having a frequency of roughly double of this one, this will be roughly triple of this one. They are not double and triple, but almost close to that. So, they are the only ones which are observed. Why so? The reason for that is two things. Firstly, the transition probabilities, because theoretically, as the selection rule permits, all transitions are possible, but the transition probabilities determines whether transition will be actually observed or not, and that depends on the transition probability. The transition probability of transitions other than these three transitions actually happen to be very, very minimal. So, they are actually not observed, or if they are there, they will be too small to be observed. That is one. And secondly, the important thing is the population part of it. What it means is that as per our Boltzmann distribution, we know that V is equal to 0 level is highly populated, and the higher levels are having lesser population. So, all transitions, because this V is equal to 1 level is almost non-populated as compared to this one. So, that means most of the molecules will be in V is equal to 0 state. That means all the transitions will originate from V is equal to 0 state. So, 0 to 1, 0 to 2 and 0 to 3, they are the predominant transitions which are expected to observe in a spectrum. So, are we going to observe only 3 signals there? The answer is no, because we have seen the spectrum earlier. There are much more number of transitions there, much more number of bands over there. So, where do they come from? Let us see. But before we get into that, let us just for a moment take a break from that and understand what is the meaning of a vibration transition. Let us understand this. This is my vibration energy level diagram which I talked to you earlier too. What is this? This tells me that I am talking about a diatomic molecule, and let us imagine like this. This is my atom number 1, this is atom number 2, this is a diatomic molecule I am talking about. And let me say, when I say this is vibrating, what it means is this is my equilibrium position of the molecule. This molecule moves like this. That is the meaning of vibration. That means equilibrium position, expands, comes back to equilibrium position, contracts, come back, expands, and continues like this. Okay. Now, suppose I hold one atom constant here and look at this one. This picture is just talking about that. This picture is talking about that I am holding one atom constant and second one I am trying to vibrate. This is just arbitrary because both of them are doing vibration like this, but for a moment if I hold it here and try to see that this executes vibration motion like this. Okay. That means when I say it is in V is equal to 0 level, that means it has the following amplitude. Let us look at the picture now. What it means is I am holding one atom constant and the second atom is moving. This is the equilibrium position here, the middle of this, but this is executing motion from here to here. So, that is the amplitude of vibration it is having here. If I give energy to the molecule gets excited over there, and what it means is I am still keeping my one atom constant. What happens is that if this molecule was this here, if I give energy to that, that becomes here and it starts executing vibration motion. And if you just are cautious enough to see that now the amplitude of vibration becomes more. In the picture we can see here that earlier this atom was moving from the equilibrium position only to this extent. This is expansion here, this is contraction. But now the extent of extension or the contraction becomes more. If I go to still higher level, it becomes still larger. That is the meaning of a vibrational transition. That means if I give energy to a molecule, it starts executing vibration, the amplitude of vibration increases, but the vibrational frequency does not change. That is a very, very fundamental thing. Vibration frequency depends only on two things. Vibration frequency, remember that omega is equal to 1 by 2 pi k by mu square root. So, that will stay as such. K has not changed, mu has not changed. The vibration frequency does not change. By giving energy to that, only thing is the amplitude of vibration changes. So, that is the meaning of a vibrational transition. Okay. Now, let us get back to what we were talking about, and we said that how do we get so many signals in the spectrum there. The reason for that is what we just discussed earlier. We talked about the three possible transitions, the fundamental, first overtone and second overtone. They primarily are for one particular mode of vibration, or for say diatomic molecule, that is only one mode there. So, we can expect 3 lines over there. But what happens is when I talk about a larger molecule, so a given large molecule has got number of bonds, and each bond will have its own vibration there. It will have its own vibration frequency because each bond will have its own bond strength and the component atoms in that will be different. So, they will have their own values of mu, accordingly they will have different vibration frequencies. So, different bonds are going to vibrate at different frequencies there, and some of them are coupled as well. We will come to that later on. So, what does it mean is that since a large molecule has got a number of bonds, they will have wide variety of vibrations possible over there. Let us try to work out what is that number which will be there for a given molecule. Now, a molecule suppose has got n atoms, it has got 3n degrees of freedom. What it means is if I have got n atoms, if I want to describe the molecule as fully as possible, I need about 3n parameters there. They are called as the degrees of freedom there. They are used for translation motion. That means the molecule is here, here or here. So, we know that any translation in the 3-dimensional space needs 3 degrees of freedom there. So, they are used for that. So, we are left with the total degrees of freedom are 3n. 3 are used for talking about the translation motion, which we are not interested in. We are interested in the vibrational motion there. So, we are left with 3n minus 3 degrees, which basically are for the rotational and vibrational motion of the molecule. And as regards the rotational motion goes, that depends on the geometry of the molecule. And we find that a linear molecule has only 2 rotational degrees of freedom, whereas a non-linear molecule has got 3 rotational degrees of freedom, which means that we are left with 3n minus 3 minus 2, or we can say 3n minus 5 degrees of freedom for a linear molecule. And for a non-linear molecule, we will have 3n minus 3 more, they are the rotational ones there. So, that means 3n minus 6 degrees of freedom for non-linear molecules, and these are the vibrational degrees of freedom. Suppose I talk about say water molecule. Water molecule is a triatomic molecule, we know that n is equal to 3. So, the total degrees of freedom are 9. Out of those 9, there are 3 are used for describing the translation motion. So, we are left with 6. Out of those 6, 3 are there for, since this is a non-linear molecule, 3 will be going for describing the rotational motion of that. So, we will be left with 3n minus 6, that is 3 degrees of freedom. That means, we can say that a water molecule can execute vibrational motion in 3 possible ways. So, they are the 3 degrees of freedom for vibrational motion or 3 vibrational modes for water molecule. So that is the meaning of vibrational modes of a given molecule. I have taken a simpler example. If you take a larger molecule, say benzene, the number of vibration modes will be much larger now, because the number of atoms in that case is 12. So 12 into 3 is 36, 36 minus 6 will be 30. So a benzene molecule can execute 30 different types of vibrational motion, and each 30 of them will have their own fundamentals, overtones and second overtones. So the number of bands which you are expecting will be much larger there. So that is how we are, basically I am trying to do here is, I am trying to rationalize that how do we get the spectrum, the IR spectrum as we actually get it. So we are trying to justify the origin of all that to be there. Okay, let us move further, and if we just sum up what we talked about in terms of the degrees of freedom or the vibration degrees of freedom for a molecule, we find that the total number of degrees of freedom will be 3n. So translation motion 3 each here, rotational motion 2 for linear, 3 for non-linear, and so on and so forth. We find the total degrees are 3n. So that is a kind of a summary of what we just discussed here. Thus we can say that the spectra for a molecule, as I just mentioned, containing n atoms is expected to have signals, fundamentals and the corresponding overtones, all identified modes of vibration. Say in, as I just mentioned, example of benzene, 30 modes. So each 30 of fundamentals and things like that, all of them are expected to be there. That means we expect the IR spectrum to be highly complex. Do we get that a complex spectrum? Let's see further. Larger the molecule, greater will be number of such bands there. In addition to all these bands, what we have is there are certain additional bands over there, and there are different varieties. Let's see what these are. One of them happens to be the combination bands, which basically, as the name suggests, they are the combination. A given combination band could be the sum of two vibrational bands there. Say nu 1 plus nu 2, the two will add together to give me some vibration frequency which will be a combination of the two. So they are also observed in the IR spectrum there. Another variety happens to be the difference band. This also is a kind of a combination. This is additive combination, this is subtractive combination. So they are also, they are called as a difference bands over there. So one is vibration frequency of a given mode, yet another one, that the difference of the two also is observed as a band in the spectrum. Then this is again very interesting observation, what is called as a Fermi resonance signals. They are very important also. They have got very significant implications in terms of the application of it. Actually, these result from the interaction of a fundamental vibration with an overtone of another vibration. What it means is, I may have one fundamental and there is some fundamental vibration whose double, that is the first overtone, happens to be close to this one. So when these two frequencies are in the neighborhood, they can undergo a resonance there. When they undergo resonance, they give rise to bands, additional bands. They are called as Fermi resonance signals. And we have a very interesting example here. That is, and this is very characteristic, one must keep it in mind, that whenever you are going to make use of IR spectrum, and if you get a doublet there, doublet means two bands over there at about 18-20 centimeter inverse and 27-20 centimeter inverse, this is very typical of the CH stretching fundamental and CH deformation bending. So these two bands, that means in case of aldehyde, that CH stretching bond, the fundamental mode of that, and CH deformation, that is a bending modes overtone, the two interact together, and what they give is two lines like this. This is typical of an aldehyde here. This is a very characteristic information which we have to keep in mind. This spectrum belongs to butyraldehyde. I just shown a bar spectrum of this. What you see is the aldehyde group is giving this particular characteristic kind of a vibration frequency there. But what you have seen so far is our discussion so far tells us that in the IR spectrum, we expect an enormous number of signals coming there, because there are so many vibrations possible there, each one of them fundamentals, overtones and all. Then there are combination bands. So we are expecting a very large number. But the actual number of bands what you observe are fewer, and there are certain reasons for that. The reasons happen to be that some fundamental frequencies, they fall outside of the region being monitored, because what you are observing is from about 650 centimeter inverse to 4000 centimeter inverse. So we may have fundamental vibration frequencies which are outside the range, we are not actually observing them, we do not see them in the spectrum there. That is one reason. Second possibility is, some of the fundamental bands may be too weak to be observed. That means they are there, but the intensity is so small that we can't even see them, they get merged with the background. Third possibility is that some fundamental vibrations are quite close and actually they overlap. That means there is one fundamental here, another band's fundamental, they happen to be on the same frequency. So, they will overlap together and give us a signal which you can't differentiate. We can't say there are two different bands, they are coming as one single band there. Yet another possibility is that some vibration modes, they are there, molecule is vibrating, but that vibration is not accompanied by any change in dipole moment. That means that mode of vibration will not absorb IR radiation, and I will not be able to see that in the IR spectrum. We saw that in case of carbon dioxide, the symmetric stretching vibration was not IR active. So, that mode of vibration will not be seen there. So, this all put together gives us the spectrum as we observe. That means the observed spectrum is actually a resultant of all the possibilities we have discussed here. So, by now I am sure that you have a feel of that how does the spectrum look like, what are its characteristics, and then how do I and where do I get all these signals from. Once we know that, then we will be in a position to later on see that how do I make use of the IR spectrum to find out the information about the molecule I want to deal with. Okay. Let us move further and see that how do I measure IR spectrum. In order to measure IR spectrum, basically what we see is that IR spectrum can be measured for all types of samples. We can do it for solids, do it for liquids, do it for gases. That means the applicability is very broad, but in principle we can do that. But doing that actually is very difficult, because handling of samples, because for any spectrum to be measured, we have to contain the sample in some container and then make it interact with the radiation there. So, the absence, there are not suitable containers are not available for that purpose. UV spectroscopy, you remember, we just take the sample, take a solution of that or a liquid sample as such, put into a cuvette, maybe a glass cuvette or a quartz cuvette, put into the sample, put into the kind of line of the radiation there, and you measure it. That is simple. But in case of IR radiation, this is not so. The reason for that is, firstly, the glass or quartz which we use very commonly, rather exclusively we use in case of UV spectrometry, that cannot be used here, because glass absorbs strongly in this region. Because our first and foremost requirement is that the container should not absorb the radiation which we are trying to monitor there, because if the container itself absorbs, then how do I get information about the molecule which I want to study there. That is one basic requirement, and since glass does not qualify to be there, so we cannot use glass at all. Even quartz cannot be used for the purpose. Second is, in case of IR spectrometry, the measurement as solution is also not easy, because most of solvents actually absorb in the region in IR spectrum. So, what will happen? My solvent also will show up there, so would my material, then the two will overlap. I will not be able to make out whether the signal is because of the sample or because of the solvent there. So, this becomes a problematic issue again. So, how do we go about it? We need some kind of special techniques for it, and that happen to be, let us talk about each one of them in terms of the kind of sample I am dealing with. Say a gaseous sample. For a gaseous sample, what we do is the sample cell, that means where I have to take my sample, actually that consists of a cylinder of glass which is closed at both the ends with a appropriate window material. Let us understand that, which is basically NaCl oblique KBr. Sodium chloride and potassium bromide, they are two very important materials from IR spectroscopy point of view, because these two materials NaCl and KBr, by and large they do not absorb in this range what we are trying to monitor there. So, in case of gas samples, what we do is we take a large tube which is made up of glass. I am keeping my gas sample in that, but the two ends there, the two windows, suppose there is a hollow tube there wherein the gas sample will come, the two windows there where my passage of radiation will take place, they happen to be of KCl, NaCl or KBr. So, they are the two windows there, and then we have some mechanism of putting the sample into the container over there. So, that is the requirement we are going to make use of here. So, typically for gas samples we use the path lengths to be large there. The reason being that the gaseous sample may be dilute there, or the samples are the ones which do not absorb very strongly. So, in that case what we do is we take recourse to a larger path length. That means we have a long kind of a container and there are two windows on that, and when they put sample into this, so because of large path length, when the radiation passes through, this meets a lot of molecules in the way and I can get a reasonably good spectrum over there. Okay. Now, let us move on to the liquid samples here. Liquid samples we deal with more often. In liquid samples what we do is, we know that the glass cannot be used, then what we do is we take help of the two salts NaCl and KBr, and they are the ones which are used for the construction of the cells. That means we use materials, these typically NaCl and KCl are used as windows in that. Let us see how do we use that. So, these cells are basically called as IR windows, and they are transparent in the region because NaCl and KBr, both of them do not absorb in IR range. Then NaCl windows are most commonly used for routine work in the region, that is a typical region we monitor here, as these are cheaper than KBr cells. KBr cells also are good, but KBr cells are expensive. So, we typically take recourse to using NaCl windows for common routine measurements there. But if we have to make measurements below 650 centimeter inverse, then we have to use KBr kind of windows there because NaCl starts absorbing in that region. So, that is the two materials we have to use in case of liquid samples. So, essentially when we say windows, what does it mean is our container is made up of these two materials. So, there are solid blocks. This is a big crystalline block of NaCl or KBr. So, the two blocks are there, and where within the two blocks we try to keep our material and put it to the path length there. So, what is done is the sample is normally taken in the form of a liquid, and we form a film by squeezing it between the two NaCl plates. That means there is one block of NaCl, another block, put a sample there, put a second block on this, and then in the process we make a very thin film in between. Thereafter, this whole thing is put into some kind of there are some mechanisms of putting the two together, and then this whole assembly is kept into the path of the IR radiation there. Then we make measurements, and there are ways of kind of manipulating or adjusting the path length. Path length can be, since we are making very thin film, it could be maybe 0.015 millimeter film also we can create, or maybe you can have larger films there, and for that we use assembly I was referring to. So, we got plates here, we put the material here, and then we can use spacers in between to increase the path length over there, and then finally the whole thing is put together, the clamps there, and we put the screws and then make that assembly which is put into the path length over there. That is with respect to the liquid samples. Let us move on to the solid samples here. The solid samples typically are studied as dispersion of the solid in a liquid or a solid matrix. What it means is that actually there are two techniques of doing that, one using a liquid matrix, one using a solid matrix, and these two techniques are called as Mull technique and pelleting. Let us understand what are these two techniques there. The Mull technique basically is one of the commonly used techniques there. In this case, what we do is we take a sample and we ground it very finely. That means you take a pestle mortar and make a very thin sample there, and then mix that with mineral oil called as Nujol, and mix it so very well that you form some kind of a paste, and this paste basically is a suspension of the material in the mineral oil there or the Nujol there, and this suspension is referred to as mull. And then this mull is pressed between the two NaCl or KBr pellets, and then this gives a very thin film of the sample between the two plates, and then that plates as before are clamped into the holder, and then the windows are open on both sides, and then this is kept into the path of the infrared beam, and then we record the spectrum. This is called as a Mull technique, very commonly used technique. So, that is basically in this case we have used a liquid matrix, that is a mineral oil or the Nujol as is typically called, is the liquid matrix for my solid sample there. The second technique called as pelleting, this basically essentially uses a solid matrix now. In this case what we do is we take a small amount of sample, say about 1 to 2 milligram, mix it with about 100 times its mass of KBr. That means you take a large amount of KBr, so about 100 milligram of that, put the two together, mix it well, again grind it well and make a fine mixture. Then this mixture is transferred to a evacuable die. There is a die there on which you keep the samples there, and then what you do is we put some vacuum on that. That means you remove all the moisture, and then we put some pressure, very high pressure is applied, whereby this mixture, the solid, the KBr and your solid material put together, that forms a very nice hard pellet, that is called as a KBr pellet. And then this pellet is put into the suitable holder, and then the whole assembly is placed in the line of IR beam, and then we record the spectrum there. So, that is called as pelleting, commonly is called as KBr pellets. That means you make KBr pellets and run the spectrum. For liquid matrix, we make a mull and run the spectrum. So, that is how typically we kind of record, we handle the samples there. So, we have seen that how do we handle gases, how do we handle liquids, how do we handle solids there. Dispersive IR spectrometer, which is the most commonly used spectrometer in the routine purposes there. Now, the principle of that is as follows, that is, this is a kind of a block diagram of a dispersive IR spectrometer. In this case, what we do is, we have a source of radiation which generates IR radiation, and then you pass the radiation on a kind of a beam splitter there. So, that part of the radiation goes through the reference here and another part goes through the sample. When it comes out of the reference, then it is fall on an attenuator, that means basically it tones down the signal and then it is made to fall on the chopper here. Do not bother about if you do not understand this terms here, because that is beyond the scope of this particular course, but I just want to give an idea about it, what basically is done. That means you take the source, get the radiation, make it pass through the reference as well as the sample, and then after that what happens is, whatever is coming out after the radiation being absorbed or otherwise, then whatever comes out, that is made to fall on some kind of a grating there. Grating is a device which disperses, that means the radiation which is coming there has a number of frequencies will be there. So, all this radiation of different frequencies of wavelengths, that is dispersed, that is the role of a monochromator, and then that dispersed radiation is made to fall on a transducer, which basically is a kind of a detector, and then thereafter certain processing takes place and what you get is a IR spectrum as we have been seeing so far. Let us sum up what we have done today. What we have done today is, we basically started by reviewing what we did in the previous session, and then thereafter we explained the origin of IR spectrum in terms of what are the energy level diagrams. Thereafter we talked about what are the selection rules, that means which determine what kind of transitions are allowed there. Then thereafter we saw that out of the allowed transitions, what are observed and what are not observed and why of it. Thereafter we worked on to that what are different possible vibration modes for a given molecule. We worked out a formula for that, that means 3n minus 5 and 3n minus 6, they are the formula for computing the vibration modes for a linear and a non-linear molecule there. Thereafter we did make a mention of that the possibility of getting other bands in the IR spectrum. We talked about the combination bands there or subtraction bands or Fermi resonance, wide variety of them. Then we even talked about certain possibilities wherein the transitions which are possible but are not observed. So, we did venture into all those discussion as well, and then we discussed the measurement of IR spectrum, and we focused a great deal on the sample handling part, because that happens to be very, very crucial in case of IR spectrometry. We talked about how do we handle gaseous samples, how do we handle liquids, and how do we talk about the handling of solid samples there. Then towards the end we briefly touched upon the principle of dispersive IR spectrometer. From here on, in the next session, what we will do is, we will try to get into the analysis of IR spectrum. We will see that what is the meaning of the fingerprint region, how do I make use of it, what are group frequencies, where do they come from, and then how do I make use of group frequencies. So, the application part of it, because by now in these two sessions we have understood the origin, the meaning and kind of an overview of IR spectrum we have got so far. Now, we will try to see that how do I put IR spectrum to use. That we will be doing in the next session. Thank you.